it says we're live. So let me just run the YouTube, make sure that we is live. Anyway, I wanted to take some time to discuss the theory. I mean, not the theory, just the fundamental assumptions that Einstein claims that we need to make, namely that the speed of time is a constant. But let me just make sure that YouTube can hear us. Nothing is happening thus far, so I don't know what's going on. It's like, what's going on? Um, really, really weird. Really, really weird. I think yesterday, as much as I waited, nothing happened. It's like we're not being recorded. We're not streaming. Mm-hmm. Mm-hmm. I don't know what's going on. Mm-hmm. Let me refresh. Oh, okay, it's better. All right, I'm gonna have to cut this to this point. All right, so let's restart. Yeah, is it working? What's going on? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. One. Okay, it sounds good. We're good. All right, let's start here. Anyway, so let's try and make it short. I don't want to spend too much time. I want to start making short videos. So let's bring out the whiteboards. All right. So Einstein. One of the things that Einstein assumed, was that the speed of light is constant. Now, every time I heard the speed of light is a constant, let me make a new whiteboard. So every time I used to hear, okay, the speed of light. Every time I used to hear that the speed of light is a constant, I used to always be surprised that this needs to even be said, because the assumption was that light, for example, is a wave. If light is a wave, then we know that waves have constant speeds. At least waves have constant speeds through a medium. So, like waves in water, right? I cannot control. Let's talk about sound waves. The speed of sound is about 300 meters per second, and I cannot control it. No matter what I do, I can yell, whisper, run towards the sound, or to the person I'm yelling towards, run away from. It doesn't matter. When I yell, there's a wave that propagates at its own speed. I cannot affect it in any way. And then the sound wave reaches the observer, and they observe the sound. But the speed of sound is a constant. Okay, so the speed of waves, so the speed of sound is a constant. The speed of saying that the speed of light is a constant is very reminiscent of a wave. And we all know that light is a wave, that basically all the particles have a wave duality. So this is very reminiscent of there must be a medium through which light and every other wave travels. Okay, that was always in my mind. I used to always be not surprised by this assumption, or by, okay, I mean, obviously. So if you're telling me the speed of light is a constant, well, obviously you're telling me light is a wave. That is the nature of waves. However, things change when you observe a moving clock. So Einstein predicted, I'm assuming that right, this has been tested, and moving clocks relative to an observer. So relative to me, a moving clock relative to me will always tick slower, which is paradoxical because that means if I'm observing a moving clock and that moving clock, let's say, is observing my moving clock and we're moving past each other, then we each see each other's clock ticking slower. But all these paradoxes are always resolved. And so forth. Wait, we can remove this, it doesn't matter. Anyway, okay. But okay, so let's assume, so in my theory in my grand unified theory, so I have come to the conclusion, you know what, forget about that conclusion. So Einstein said, let's assume that there is a two mirrors, a clock. This is Einstein's thought experiment clock. So Einstein said, let's imagine a clock, and let's imagine a photon that is like a particle bouncing back and forth between these two mirrors. And he continues with the thought experiment. So this is already very confusing. Why would, because this is a particle of light, this is a photon. So if this is a photon and the photon is bouncing up and down on this between these two mirrors, Einstein says, let's assume the assumption is every inertial observer is going to see this photon moving at the speed of light c. So everyone is going to measure this photon moving at the speed of light, 300 million meters per second. So even if this clock starts moving and we measure it over here, and we know that if the clock can, right, if the clock moves to here and then to here, then Einstein said what's bound to happen is that this, let's do it with the red, this photon is going to bounce to here. It's going to bounce from here. From here, let's say from here to here. So it's going to bounce, tuck, 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 tuck. It's going to bounce from here to here. That's the arrow. Then it's going to bounce from here to here. So Einstein predicted that the clock is going to tick slower in reference to an inertial observer. So Einstein predicted that an inertial observer, since the speed of light, if we assume the speed of light is a constant, then an inertial observer that is not moving in reference to the moving clock will see the ticking slow down. So because the speed of light is a constant, and because the photon needs to travel a larger distance, so here it was doing the distance very quickly. Everybody knows the shortest path is a straight line, but here the photon is not taking a straight line. I mean, well, the distance is greater. I shouldn't say about the straight line. The distance now becomes much greater, and since the photon has a constant speed c, then of course the ticking will have to slow down. All right. But the question is, if I just assume, right, I claim we don't need to assume this constant speed of light. We can reproduce this experiment in water or with sound. We can reproduce this in any wave. Every and any wave will reproduce this experiment. There's nothing special about light that a moving clock ticks slower in relative to an inertial frame of reference. Let's run this experiment. Let's prove it. So let's run this now in water. Let's assume that this is in water, but instead of a photon, let's assume it's let's say it's a sound wave in water. But before that, let me just make a remark before that. So I never understood, and I don't think this can be understood. This thought experiment cannot be understood because just saying that we assume the speed of light is a constant to run this thought experiment is not enough. You also need this photon to behave very, very weirdly. So, as a particle, how does it know to move with the clock and hit right? So here it was moving up and down. When the clock started moving, this clock, the photon suddenly knew to move forward with the clock and continue to move forward. And if the clock stopped here, the photon would know to stop. How is this possible? What kind of a genius photon is this? So even the thought experiment doesn't make any sense. A. And B, why would the photon have a constant speed of light? A constant speed? Where does it come from? What causes this? So basically, my accusation. This is going to be. I've come to the conclusion that we need to abandon Einstein, at least partially. So Einstein made a few mistakes in his life that people have caught these mistakes. But some mistakes he made that people have not caught these mistakes, and these mistakes have been now ingrained in the zeitgeist, in the pattern of thought that all intellectuals are immersed in and are exhibiting. So everybody today is afraid to go against Einstein. To say that Einstein was wrong is like it's like for a religious person to talk about God. The God is wrong. How can you say God is wrong? You cannot say that, you're heretic. So I think people today are terrified of saying that, even if they're not aware of it. It's like Einstein was a genius. You're never going to be a genius like Einstein. Even though we know that Einstein made mistakes and people caught his mistakes time and time again. I mean, it's not like he was like beyond humanity. Einstein was a communist. I mean, that's pretty dumb. You got to be pretty dumb to be a communist. Anyway, so I don't know if he was a genius. We know that he was a pretty bad student. I don't know if he was a genius. I don't know. I don't know. So I heard today a lecture about him that he wasn't a genius. He was just very good with his imagination. He could create thought experiments like no one could. And those thought experiments gave him his superpowers. It's not his math. He was not a good mathematician. That's what I heard. I'll be the last one to judge. I mean, I'm definitely not anything to write home about. However, I am very good at thought experiments. I'm pretty good with that. So thought experiments, I'm pretty good at. Everything else, not so much. So anyway, that was a preamble to let you know that usually I love Einstein and I still love him and I probably always will love him because he gave us so much. He gave us so much. However, Einstein, in his theory of special relativity is not a theory according to my proposition 90. So let's go to proposition 90 and revisit proposition 90, the definition of a proper scientific theory. Let's see that it's still written in accordance to my current belief. So this is proposition 90. If a proposition is not scientific, then it is invalid. That goes without saying. Unscientific is not part of reality. That goes without saying. If a proposition is not, if it's unscientific, the whole right scientific just means reality, and reality is scientific. These two are just synonyms. If we cannot perceive it, then it is not real by definition, right? So the definition of real is that we can perceive it. So far, so good. Except for this proposition, right? This proposition is not a good proposition by this definition, but that's allowed. This is allowed because of the incompleteness theorem, at least my incompleteness theorem, that no system can be groundless. No system can exist without a set of axioms. And axioms are assumptions, and assumptions are lies. Lies that we claim to be true. Lies that we either cannot prove or have not proved or don't want to prove or are too tired to prove or right? Choose one of the above. But if you assume something is true that you're not sure is true, that's called a lie. And if you do it with intent, that's called a lie. That's, usually it's a crime. If you do it in court. But okay. But that's allowed. So, and according to incompleteness, we can have, that's fine. We can have a set of axioms. We declare these to be axioms. It's fine. All right. So this is the axiom, basically, that says, okay, let's continue. I don't want to get bogged down with Proposition 90. All right. A scientific theory is a simple. Okay. I'm not going to take away from Einstein. His scientific theory is relatively simple, understandable. And here we're getting into a little bit of hot water with special relativity. Understandable. Specifically, the speed of light being a constant. If you have a ping pong, like a photon, or a photon is like a ping pong, it's a particle, why would it always have a constant speed of light? I cannot understand that. It's a simple notion, so it fulfills simplicity, but it's not understandable. I don't understand. I mean, I understand that you're saying it, but why? Why would you say that? So maybe we should say reasonable. It has to be understandable and reasonable, meaning you have to give a reason for the theory. The theory is supposed to be a reason for something, because I already said we can peel one layer of the onion at one time. So every theory is always going to have an assumption, because you're only peeling one layer of the onion of unknown. You can't. It's difficult enough to peel one. I wish we peeled one and do it at a constant rate, but I don't think we even. I think we stopped peeling. I think what we've done is gone in reverse, and we're adding layers onto the onions. Anyway. Anyway, I don't know. I don't know if I would call it a scientific theory. Okay, model of an observed phenomenon. Well, Einstein made a prediction. I don't think he mentioned any phenomenon. Like, I think he was responding to the Michelson-Morley experiment, that the speed of light is a constant, but he doesn't mention it. He doesn't mention it that he's going to come and explain it. It feels to me like he came to explain it, that we cannot explain. A model is a three-dimensional mechanical contraption. So has Einstein fulfilled this in his theory? I don't think so, no. There's no mechanical contraption. He just gave us rules. Rules are not a mechanical contraption. No, but his thought experiment, we can, based on, if we take his rules for granted, then we can, of course, reproduce his theory. So I don't know. That we can easily build, this is wrong, it's built, or that can be easily built or programmed into a computer simulation. And there are computer simulations of special relativity or mathematical equations such as in general relativity. I don't know, in special relativity, yeah, there's a mathematical framework. There's no problem. Okay, however, so I don't know what to do. I don't know if I should reject and call Einstein unscientific. Let me tell you my explanation. So, of course, I don't know. I've come to this conclusion from many directions. Now I'm coming it from special relativity. So I would start from Michelson Morley because I need, according to my science, the way I define science, I need to start from a phenomenon that we've noticed that we cannot explain. And Michelson Morley was not explainable. Somebody needed to come and explain. Not just that, when everybody teaches Einstein special relativity, they always start from the ether, Michelson Morley, and special relativity Einstein. So everybody sees the relationship. Michelson Morley came to talk about the ether, find out the ether. They wanted to just find the ether. So maybe what we should do is we should explain the ether. We should explain their results, that their results do not contradict the ether. There's no contradiction to the ether. Let's try and do that. And then we'll see that the special theory of relativity is not a theory. It's a framework that we can use once we understand the mechanical explanation to the Michelson-Morley experiment. But we shouldn't start from an assumption. We need to let's I don't know what to do. Okay, let me do the simplest, maybe the simplest part first. I'll go with what I know the best first, and then we'll work out all the details slowly. All right, the first step. So this theory of Einstein starts with this weird thought experiment. So I don't even know why you would have such a weird thought experiment. Why would you think of a particle of light? Why would you do that? That complicates the experiment because now the clock has to be smart. The photon needs to be smart to know how to bounce perfectly. Like here it's bouncing perfectly and here it's bouncing. How do you do that? That's weird. So it's a weird thought experiment. The next problem with this thought experiment is why would a particle have a constant speed? We've never seen a particle with a constant speed. Particles usually are at rest. And you can fire them at literally any speed you want. Why would a particle of light have a special speed? That doesn't make any sense. That's unreasonable. Anyway, okay, so because of that, I came to the conclusion that we can better run this thought experiment with a wave of light, which makes much more sense. So the wave of light, let's maybe use, I don't know what color, purple. So a wave of light, so a wave means that there's a three-dimensional, of course, waves are three-dimensional propagation of a wave, and it propagates and propagates. Oh my God, Jesus! And it propagates. Yeah, it's very difficult to draw. So I'll just draw almost straight lines. It propagates and propagates, and then it hits the opposite mirror and bounces back. And what happens when you go sideways? Well, when you go sideways, it's a three-dimensional wave. So of course it's going to go in as spheres from the source. So it's going to travel naturally to every direction. And naturally it's going to interact with the opposite mirror. It's going to interact. Once it interacts, it even, it's going to be again, it's going to be, let's do a different color, maybe yellow. It's going to be waves, three-dimensional spheres coming, a three-dimensional sphere coming out of this. As part of that, it will travel and interact with either the mirror or the detector. It's going to tick. It's going to tick. So the thought experiment is, it's on better footings, better grounds. All right, that's the first thing. Second thing that we get for free when we just switch to a wave is the speed of a wave. So a wave has or the constant speed, right? So before we couldn't, when we think of light as a particle, so why would you choose a constant speed for a particle? That never happens in nature. But as a wave, waves always have a constant speed. It just depends on the medium. So fantastic. So now we get a constant speed of light, c. And c, you could say, stands for constant. Of course, it doesn't stand for something else in Greek or something. Anyway, so you get the speed of light, and now everything, the thought experiment is much simpler. It makes much more sense. And now you don't even need to assume this constant speed of light. First of all, you get constant speed because it's a wave in a medium. And we already know the speed of light. The speed of light is c. So it's done and done and done. We get everything purely from intuition. Before this experiment was unintuitive. A particle knows how to travel and has a constant speed that's completely unintuitive. Why would you go there? Anyway, I don't know. I don't know Einstein. I don't think anyone knows how he came up with this thought experiment. It's like really weird, really weird. Anywho, okay, let's continue. So, but why? So would everyone recognize? So, but hold on. So we see a moving clock ticking slower. Would we see this? Is this true? Let's assume that there's a medium, that there's like air or water. Let's assume there's water. That this thing is immersed in water. Okay, so now it's not going to be light. Let's now go and talk about sound waves in water. So you make a sound. So let's say this is a real clock with two mirrors, but they're acoustic mirrors. So the light or the sound bounces. It just bounces. So, and there's a detector every time the clock makes a tick and hears it here. There's a sensor that hears it. And again, it makes a sound, tick. And there's a sensor here that hears the tick. And maybe flashes a light so we can see it. So would we see this clock ticking as it moves through water? And the answer is, of course. Of course this clock would slow down if it moves in water. It's like the theory of relativity, there's nothing to it. If you just assume we are immersed in water that we cannot, for some reason, interact with. We'll get to that, why we cannot, well, we're having a hard time interacting with it. So it's very difficult to see this water. I'll grant you that. It's much easier to imagine that there is nothing, that there is just air and there's a vacuum in space. And that's why the planets are moving and they never lose speed. Yeah, I'll grant you it's difficult to believe that there is a liquid filling the universe. It's definitely it's I grant you that you cannot touch it. When you move your hand in space, you don't feel water. I'll grant you that. However, you have to explain Michelson-Morley. You cannot avoid Michelson-Morley. Okay, next problem. So Michelson-Morley. So first of all, we're able to slow down a clock. I don't like saying slow down time. No one is slowing down time. That's a ridiculous statement. Time is a macro illusion of it's a macro illusion. There's no time. There's no particles of time. Time doesn't exist. Time, we can measure time. Time is a phenomenon. We can measure it with clocks. There's a way to measure time. Yeah, but time is not some fundamental part of the universe. Well, nothing is, I guess. Okay, so the next step is so we're able to easily slow down a moving clock in water. A moving sound clock, easily we can show is slowing down in right when it's moving through the medium. Great. Great. Okay, next problem is the Michelson-Morley experiment. Now this is more complicated. So how do you explain the Michelson-Morley experiment? How do you explain that, Mister? Hey, Mister. How do you explain the Michelson? Okay, what is the Michelson-Morley experiment? It's actually it's a very simple experiment. So Michelson and Morley, they set out to find these particles because if you notice in the previous discussion, it's difficult to see very, but I drew these particles. The discussion is based on these particles. That this is like a fluid. There's water in space or everywhere. There's this fluid that light waves travel through and planets move through. And I agree it's difficult to believe, but I assumed that it exists. Michelson and Morley, circa 1900 or something, they set out to find out they call it the ether. They called it the ether, and waves that move through the ether, they called ether waves. And radio was ether waves. Did they have a radio in 1900? Probably. I guess. Like, I think it used to be in the old days. They used to call radio and television the ether waves because I think it's for historic reason. People used to believe in this ether. It was obvious to the ancient scientists, meaning before Michelson and Morley, everyone agreed that this ether must be there. The Maxwell's equations, for them, it's obvious that there is an ether. It's straightforward. The conclusions of Michelson and Morley is that light is a wave through some medium. They knew some properties of this medium, such as the speed of waves through this medium, which was the speed of light, which made everyone immediately, I think Maxwell realized it first. He said, oh, then light is an electromagnetic wave, just like the rest, just like, that's what his equations describe electromagnetic waves. They move at the speed of light c. Therefore, it's measurable. He measured, or he didn't measure, but he predicted, or from his equations, from the math, it came out the speed of light is the speed of electromagnetic waves, which means electromagnetic waves are just light. Light is electromagnetic waves. Very nice. So these are the ether waves. I think everyone used to believe in ether. But then came Einstein, and Einstein told everyone there is no ether. Here, I can explain to you everything without the ether. And everyone said, fantastic. You're making life simple for us because we cannot explain Michelson Morley. And now you finally gave us the explanation. We cannot explain, and I'll get to Michelson and Morley and I'll show you. Hopefully, I can show you. I've never tried this before, so I don't know if I'll succeed. But everyone couldn't explain Michelson and Morley experiment. So everyone, I don't know the reason, but since then, you're not allowed to say the word ether. If you talk to scientists, physicists today, and say ether, they would laugh at you. And I've tried that, and I didn't even say ether. I just said there is a fabric from general relativity. The response is, it sounds like you believe in ether. It sounds like you're like basically a creationist or a flat earther. Basically, it's like it's been proven with beyond the shadow of any doubt that the ether doesn't exist. That the light moves or is mediated by a vacuum. which doesn't make any sense and is unscientific. It's an unscientific statement, but fine. Fine. All right. Anyway, so Michelson and Morley set to find out anything they could about this ether. So they assumed, their assumption was, if I understood it correctly, that there is a sun here, and here is the ellipse that the Earth revolves around the sun, and here is the Earth. The Earth is here. So if we assume that there is this ether running around, then either there is a wind of ether, or it's stationary, but stationary relative to what? Or wind relative to what? So they didn't know. But they assumed whatever it is, the Earth sometimes moves in this direction, but sometimes it moves in this direction through the ether, and sometimes the Earth moves in this direction through the ether, and sometimes the Earth moves in this direction. They assumed that the ether, whatever it is, it's either stationary relative to the sun, or it's moving to the right, moving to the left, moving up. Now, whatever it's doing should be, they assumed it's constant. They did not assume that the ether happens to surround Earth and happens to always move with Earth. That's very irrational to assume that. All right, I agree with them that they made a rational assumption. Very, very nice. Let's continue. All right, so this is the premise of the Michelson-Morley experiment. All right, the next step of the Michelson and Morley team, they said, all right, let's sit down in our laboratory and we'll do the following. Now, this is a top view. 1 second, do I have a message? No message. Let me just see if my favorite person in the universe is, oh my God, she's still sleeping. Wow. Oh my God, that's really great. I'm so happy. Wow. Let's continue. Let us continue. All right, so the setup of the Michelson-Morley experiment. Of course, everyone who knows the Michelson-Morley experiment, they can explain it to me. I know very little about it. All right, let's try and run the Michelson-Morley thought experiment. Okay, so, what do we got? So they said, all right, so this is a top view. So they said, let's assume the ether is going to come in this way, right? It's either going to come in this way, it's going to come from one direction or the other, but it's going to come in this way and leave this way. Let's make this assumption. Let's assume that's true. So if that's true, so the ether, so if that's the direction of the ether, that must mean that a light ray, right? So we're assuming that that light moves through the ether. That means that a light ray moving that way is going to be slower, right? Because it has to travel upstream relative to a light beam going this way, because it's moving downstream. So of course this should move at a faster C plus, and this should be C minus. This should be just under C, and this should be just over C. So if we take some distance x and the same distance x here, we should be able, oh my God, I'm so sorry. We should be able to see, for example, that this takes just a little bit longer. Let's say some time t. It takes some time t. This is distance x, and this is distance x. same distance. This will take just a little bit. This will take, if we assume this takes time t, then this should take less than time t, t minus t, just a little bit under t. It should take less time. It should do it faster because it's moving with the current. It's like they assumed it's like water. They said, okay, let's assume, right? If we did this experiment with water, with sound wave and water, right? Imagine we ran this experiment with this is water, and these are sound waves, but there is a stream. So imagine the stream is going with the green arrows. The green arrows is the motion of the stream, of the particles of the ether, the particles of the water. Right? So if we assumed that it's water moving through, and that was basically what everybody assumed before Einstein, that the ether is like a liquid or a gas. They called it, like, ether means like a gas. Which is another reason I don't like, which is a reason I don't like the word ether, because it makes it sound like it's a gas. And that's not what it feels like to me when you think about what is holding the galaxies, what's binding the universe, what's binding the galaxies, what's binding the stars. These are not gases cannot do it. There's something much more rigid binding the earth to me right now. A gas wouldn't do the job. All right, let's continue. How long? I just want to make the point and go home. It's called GH. Go home. So I just want to finish quickly and go and make it a short video. So we've been doing videoing for 42 minutes. Hopefully we can finish in under an hour. All right. So what I'm saying, obviously, what I'm saying is I would say, certainly when I talk about sound waves in water, everyone agrees, right? When I said this about sound wave in water, I'm not saying anything unscientific. And when I talk about light waves in if I say light is a wave, again, this makes perfect sense, which everybody agrees with, right? I'm not saying anything weird here, that light is a wave. I'm not saying anything weird here. I don't need these particles. I don't think I need these particles. I mean, everyone agrees that light can travel in a vacuum, so I don't need these particles. That's not. But I do. I mean, everyone agrees that I don't, except for me. I disagree that I don't need it. That's ridiculous. How can you say you can have a wave without a medium? So I need these particles. So I'm going to remove the X. I need these particles. And I want to show you how you can have these particles and eat. You can eat the cake and have it too. You can have the particles. You can have the ether. You can have a fabric. It could be a rigid liquid and special and general relativity and quantum mechanics. Everything works just fine. I would say even better than always, because it's much more natural. No longer do I need to ask a question, because every time whenever I hear scientists talking, physicists talking, I'm like, I want to rip my hair out. What are you talking about? Obviously, you're wrong. Obviously, what you're saying is nonsense. It's unscientific. How can you have a wave through a vacuum? That makes no sense. How could the Earth be bound to the moon through a vacuum? Newton says that makes no sense. So anyway, but I need these particles because to me, because I need my proposition 90 to be scientific. I need to build a three-dimensional model. I need to be able to build a mechanical contraption. I cannot have the universe be held together by allegories and analogies. None of that. I need to know that there is mechanical principles, simple, straightforward mechanical principles, intuitive principles holding us together. Let me see. I just got a message. Let me check. It's not important. Not important. Not important. It's good. It's good. Let us continue. Let us continue. All right. Yeah, let me click it. Okay, so we talked about the Earth and this. So I believe we need to find these particles, and we we should have no issue with these particles. Oh yeah, I wanted to go to the Michelson Morley. So we started from this, and we spoke about the right the natural thought. The natural thought, the intuitive thought is that there must be a fluid or a gas. There must be a medium that mediates light. All right. So we said, okay. So I'm just tracing back the steps, and I'm tracing back the steps of today. Oh, tracing back the steps that we went through today. Let me just undo this, and which in which I'm tracing back the steps of history as much as I can. Okay, because what I think I've discovered is both something in physics, in philosophy, philosophy of science, but also in history. So I think the world, the science took a wrong turn when Einstein came along. Einstein was like people for some reason worshipped him, and he was worshipped. So people said he can't be wrong. He's got to be right because everyone is worshiping him. And Einstein said, I can't be wrong because everybody's worshiping me. They can't be wrong. So there's this interdependence, that there's this coupling system. This is like a psychological phenomenon. This is why it's so dangerous to become famous. Like, if you want to lose objectivity, just become famous. Because we know that famous people are just detached from the people, and they become detached from reality. So this is what happened to Einstein, and this is what happened to science. And this is where science went like straight off the path, the beaten path. Science used to be done by rich people, that they could sit at home and think and study and do their experiments, and they had the budget, and the scientists were wealthy people. But more important, they were objective because they were self-funded. They couldn't care less about anything in the universe except for the universe. They really were curious about the universe. And then came the new age of scientists, the government scientists. I think Planck was already a government scientist. Einstein tried to become a government scientist, and he basically struggled. And so this is the age of the bad, where bad science started to take over. Government science, government funded science, politicians, politics, and scientists had to become part of the politics, basically politicians. And the now scientists had to bow down to the politicians to get budgets, to get their positions, to get their funding. So this is the time that science started veering off the path of the old science, the objective science, the gentleman science and gentlewoman. But science, the objective science. Now I don't think you have to be rich, because especially nowadays, everybody can sit at home and live in, somewhat comfortably with with very little. People can sit at home a lot of hours and dedicate themselves to any science they want, because we live in the age of hobbies. Everyone has a hobby, time for a hobby. Everyone goes to the gym and people do jujitsu and MMA, like stuff that like very few people used to do in the past. Today, everyone does so much. Everyone is like enjoying their freedom. So I think everyone today can become a good objective scientist and avoid becoming a government. Do your best. Never become a government scientist. But also, I would say try not to become famous because it's a trap. So I think what happened, this is my theory. So I think what happened is Einstein became famous. He became trapped in his, there's infamy. What do you call it? Fame, in his fame, yeah. He became trapped in his fame and he could no longer think logically. Let me just check the audio. Yeah, the audio sounds good. All right, this is it's a good lecture, but let's continue. We got stuck with history of how I view the evolution of science. All right, so let's talk about the Michelson Morley. So Michelson and Morley, they said, let me just move it. They said, all right, so let's talk about water. They said. I don't think they said, but it's obvious. I think it was obvious to them. But let me make it obvious to you. So they said, if they would have said, if we ran this thing underwater, and let's assume there is a green stream of water this way, and we fire a sound wave in the blue this way, over a distance x here and a distance same distance x, and here we fire the sound wave downstream, and here on the right we fire the sound wave upstream over the same distance. Well, if this is taking time t for the signal to travel upstream, and you can imagine that if the speed of sound is c, if the speed of the stream is the speed of sound, then you get a black hole, right? And here already you can see, hey, you get a black hole for free. So even black holes come out of this very simple theory. It's so simple. It's ridiculously simple. So yeah, it's so completely mechanical. Okay, let's continue. So if this upstream takes sound, so let's say this is the stream is less than the speed of sound. C here, when we're talking about water, C is the speed of sound. So if we have a detector here to hear when the tick arrives here, let's say it took t. Well, then if the stream is going to the left and we fire downstream, then of course we expect the signal to arrive at under t, less than the time required to go upstream. That's pretty obvious. Fantastic. Okay, so Michelson and Morley, they said, let's assume the same about light. Instead of the signal of sound in water, it's going to be the signal of light through the ether. And they assumed, well, the ether is going through us right now. It's fine. It's tiny particles. At this point, I think they knew that there's plenty of tiny stuff moving through them. I think at this point they knew about X-rays and stuff like that, and neutrons and radiation. I think they knew already about radiation at this point. So they knew that things can move right through us and we wouldn't know it. So that should not have been an issue. So they said, okay, obviously there's these particles, otherwise, what is light waving through? All right, so they set the experiment. So how do they set this experiment? So they said, okay, so this is going to be a little bit confusing because I've never really looked into their experiment in detail. So the light, so they're going to fire the light this way. But they don't know which way the stream is going. They put a mirror here, semi-translucent mirror, which means that the light, let's use purple. So the light, when it's going to hit the mirror, it's both going to bounce to the side and it's going to continue forward. It's both going to do, it's going to split the beam in two. And here there's going to be a mirror. And here there's going to be a mirror. And this signal, then let's make it, let's go with red. No, red is the contraption. Okay. This signal from here, let's say it's going to arrive here. This is the final point, detection. And this signal is going to come back. Wait a minute. If it comes back, okay, I think it makes a little bit of sense. But let's use another color. Let's use green. So it's going to come back to here. So let's see if this makes any sense. So what they're trying to do is they're trying to compare. There's so few colors in the universe. Come to think of it, it's like I've used everything. RG. Oh, maybe this one, like sort of pinkish. So what are they trying to compare? They're trying to compare assuming green, assuming stream from right to left. So they're saying, okay, this is the difference, right? Both, right, over here, both beams. When I say both beams, I mean both of these. So both beams are traveling through the first part. So that's not going to be the symmetry breaking part. We're looking for symmetry breaking so that we're comparing two different things. All right. So the symmetry breaking is that the beam splits and one part goes on my paper right now is up and down, but it's not affected by the direction of the stream. So it should not move any faster because it's orthogonal. It's in 90 degrees to the stream, so it should not be sped up by the stream. Okay, but wait, what about this guy? If it moves this way and then back, has it really? I don't know. Has it? Oh, and this is the price I pay for not paying attention every time I heard the explanation to the Michelson-Morley experiment. So for some reason, because this is downstream, but this is upstream, so I don't think they compensate for each other. This should go fast. Like if we assume I can't even stop to go listen to an explanation, but that's what I'm going to have to do. But I want to keep it short. All right, that's a good place to stop. Let's stop here. We'll do a part two. Unfortunately, I wanted to show you because I have in mind how to solve the problems, but we need to do it methodically. So let's stop here. We'll continue next time. All right. Thank you. See you next time. Bye.